So in this video, I'm going to go over the properties of the electrostatic properties of a point particle in 3 dimensions. And I'm going to show you basically how this result is digitalized or formalized into this project called PhysLean. So PhysLean is a project to formalize physics into this interactive theorem prover called Lean. And basically it means that you are guaranteed to write statements which are mathematically correct, because you can only write statements that are mathematically correct into one of these interactive theorem provers. And PhysLean is an open source project to write results into Lean. I may have already said that, and I apologize if I said that twice. So, like I said, we're going to look at the electrostatics of a point particle in 3 dimensions. So that's basically where you have a particle sitting at some location R0, and you have an electric field going away from that particle, basically because it has some charge Q. So within PhysLean, over on the right hand side of my screen, this is within this PhysLean file, and it is in electromagnetism, naturally, electrostatics, 3 dimensions, and point particle. So the first thing that we define in PhysLean is the charge distribution of that particle. So this is this definition here, and we scroll over to the right, and we see that the charge distribution is just the Dirac delta function. So let me write that here on the left-hand side of the screen. The charge distribution, given a charge Q and a point R0, so R0 is the point where the particle is, this is equal to Q times by the Dirac delta function at R0. And a physicist would write this as follows. They would usually write this as a function. So they'll take some quantity R, and they'll say that this is equal to the Dirac delta function minus R0. I'm going to put that in a box, basically because this is not really mathematically correct. This lower statement is not mathematically correct, what this statement is. And the reason behind this is that delta is a distribution. Not a function. So what is a distribution? And I'm going to go over a bit about what distributions are, basically because they're very important when you're dealing with electrostatics and you're trying to do things properly, because if you don't do it properly, if you don't do it, with distributions, you won't be able to prove things formally. So let's do an aside on distributions. And we can go over to PhysLean to see how they have defined distributions there. So we go into mathematics, we go into distribution, and we go into basic. And we see down here, this is the definition of a distribution. Really, we're focusing on this line here. Bit cryptic, so let me go over and explain what the definition of a distribution is. I can perhaps slide this over a bit. So let's say we're trying to write a distribution that corresponds, or that kind of represents or is similar to a function from R cubed to R. And this is really kind of what this Dirac delta function is, but it's not a function, it is instead a distribution. So how would we do that? Well, we would define the space R cubed R of functions, and this is the space of nice functions. That's obviously not a technical term and not a mathematical definition. But what that really means is that they are smooth and they decay rapidly. So when a physicist often says, let's assume this function is smooth, it decays at infinity, kind of often assuming they are live in this space. And this is sometimes called the Schwartz space, and the functions in it are sometimes called Schwartz maps. So what a distribution is, it is a linear map from the Schwartz space, which is a vector space, to 2, in this case, because we have R here, this would be R. But let's say we had Rn here, this would be Rn, but this R here would just be R. And this is a linear map, and it has to be continuous. So linear and continuous. And that is what a general distribution is. It's just a linear continuous map from this space of Schwarz maps to Rn. And this is what we have here, where this notation, let me see if I can highlight it, this notation here, this arrow with this arrow here with this L and this box basically is a linear continuous map. This is what this is saying. So let me give you some examples of distribution. This distribution delta R0 takes in a Schwarz map, and that's just basically a function that's particularly nice. We usually call it eta, and it outputs eta evaluated at R0. Now what a physicist would write is the following for this exact same thing. But this is really just syntactical sugar. Really, you should think of this delta function as a map in its own right. Another type of distribution is if you are given a function, r cubed to r, well, let's say r cubed to rn, let's say we're working in this setting here, then we can define the distribution, let me call it f with a box around it, that maps eta to the integral of eta r f of r. And this is really how you consider a function as a distribution. But f has to satisfy some nice conditions. And that's basically that is not too crazy. Basically, less strict conditions than on the Schwarz maps, but it has to satisfy some conditions. And examples of functions that do satisfy these conditions are things like 1 over r cubed times by over r, in the case of like what we'll see today, basically. Things like the modulus of r, etc., etc. Good. So that really concludes our aside on distributions, and we're going to use distributions because a lot of what we're going to be doing today is going to be secretly working with distributions. So like I said, we kind of have to do this basically because we're using a direct delta function, and if you want to use a direct delta function, you have to work with distributions. So let's go back to this electrostatics file, and I should say at this point that if you ever want to get involved with PhysLean and help in write documentation, please do. There's lots to be done, and any help is amazing. So, right, so we've written down this distribution, and our distribution is this thing here. Do a little bubble around it. And this was in this line 40. So we then have a couple of lemmas within PhysLean, and these are simple lemmas. They're basically saying, let's say we take the distribution, and we take it at, when the charge is 0, that distribution is just going to be 0. And this is what this lemma here says. And this one here basically says that the distribution at R0 is the translation of the distribution at 0. And this is notation that I'm going to use for the translation operator. Very generically, within PhysLean, the translation operator is this thing here, the space translate D operator. I'm not sure I can highlight that without the box coming above it, but that is the translation operator within PhysLean. So let's talk about the electrostatic potential. So the potential. Now, I'm not going to derive any of these just yet. So what I'm going to do is I'm going to state the electrostatic potential, and I'm going to state the electric field of a point particle, and we will prove that they are correct in a second. So the electrostatic potential is the following within PhysLean. So let me write it down first. I'm going to get my Q's and my R's the right way around. This is equal to the distribution corresponding to the following function. Q over 4 pi epsilon, where epsilon is your permittivity, over the difference or the distance between R and R0, where remember R0 is the place where the particle is sat, and R is the function or the variable that this is a function of. And this is exactly what's written here. So this electrostatic potential is a distribution. So let me highlight this. It's a distribution from a function, and that function is given by this thing here. Let me highlight this thing here. And then what follows in these lines here is basically a proof of results, basically saying, okay, this first one is saying that this function is sufficiently bounded as r goes to 0 and as r goes to infinity. And this one is saying that it has some integrability properties. So again, we can start to prove some properties about this electrostatic potential, in particular this one here. And this is very similar to the one we had above. It basically says that the electrostatic potential at R0 is equal to the translation of the electrostatic potential at 0. And this translation operator is really defined formally for distributions in a very rigorous and easy to understand way. So basically, if you have a distribution D, for example, the translation of that operator acting on eta is equal to the distribution acting on eta, let me actually call this R0 down here, of R, where you translated this function by R0 in the opposite direction. And that's basically how this distribution, how this translation operator works. You basically, and how really all operators on distributions work, you really act on the Schwarz maps instead of the distribution itself in the opposite way. So let's talk about the electric field. And that's really the thing we're all here for. Well, hopefully you're all here for the lean, but if not, hopefully you're here for the electric field. What is the electric field? So the electric field is again the distribution corresponding to a function. And what is that function? So this function takes r as an input, and it is q over 4 pi epsilon. And I'm basically just reading off here at this point, times by r minus r naught cubed, and this is all times by r minus r naught. So this is actually a vector quantity, and this should be considered as a function of r. So again, this satisfies that this is a proof here. These couple of lines here are basically a proof that this function, this function satisfies the necessary properties that it can be made into a distribution. But let me give you a little hint. If this 3 here was replaced with a 4, you would not be able to prove those properties. In fact, the fact that this is a 3 basically is the limiting case where you can take such a function and write it as a distribution. And again, there are some nice properties. So the electric field for Q equals 0 is obviously equal to 0, and the electric field at Q equals R0 is the translation of the electric field at Q0. And you may be wondering, Joe, why are you so caring about these translations? Well, basically, they're going to save us a lot of work in what's going to come, because we are going to focus on the case when R0 equals 0, and then we will generalize to the case when R0 is not equal to 0. So now we want to prove something, and you can see here, because I've written the word, we're going to prove. I'm never sure whether I get proof and prove the right way around, and I apologize that is confusing. So we're now going to prove the following result. Well, let me write this as a theorem, actually. So the theorem that we're going to prove is that Q at R0 is equal to minus the gradient of the potential. So the electric field is equal to the negative of the gradient of the electric potential. And this is what you would expect. So we're going to prove that, and we're going to show that is true. And let me just show you basically where the proof starts. So the proof starts on line 102, and it goes all the way down. It's kind of long. It keeps going. It finishes. Let's keep on going. Oh, no, I think I've gone too far. It finishes here. So it's 400 lines of lean code, and it's probably like a page and a half of text. But this is properly formal, completely rigorous proof that this statement is true for the potential, the electric field that I've given you here, and the electric potential that I've given you here. I'm obviously not going to go over every single little detail here, but let me give you the brief idea of the proof. So the brief idea of the proof is to first prove it for the case of R0 equals 0. So this is this case, so step 1. And then step 2, once you've got that, is to, obviously step 1 is tricky and involves a lot of other steps, but then step 2 after that is to use the fact that the translation operator basically commutes. So if we want to prove this here, we do the following. We go that this is equal to the translation operator epsilon phi 0, and then you can show that the translation operator commutes with the gradient, and this is equal to obviously the translation operator minus delta phi q0, and that is equal to tr0 eq0, and then we kind of showed that this is equal to this thing here earlier. So that kind of does the general case where the particle is at a random location. So we need to focus on this case here when the particle is at 0. So what does it mean that this thing here is true in terms of distributions? Well, let me be nice to myself. Let me drop the zeros from now on, because we're just going to work in the 0 case. Let me get my eraser. And let me drop the q's. We're just going to keep them implicit. So what this really means is that these acting on a Schwarz map eta, so for all eta really, this is true if and only if, for all eta, so for all Schwarz maps, E acting on eta is equal to the minus of the gradient of phi acting on eta. And I haven't defined this gradient, but we will see what it is in a second. So let me write down what these correspond to. So remember, this is the electric field, and this is the electric potential, and this was how we defined a distribution in terms of a function. So what does this correspond to? The left-hand side is simply equal to the following. So this is equal to, I'm going to actually have to remind myself by scrolling up on the right-hand side what the electric field is. So this is equal to Q over 4 pi epsilon times by R minus R naught times by R minus R naught times by eta of R. So that's the left-hand side, and then this right-hand side, and that's really by definition. So that is definitionally equal to this. And then the right-hand side is equal to the following. So how this gradient is defined? Well, it's actually defined in a fairly tricky way. So I'm not going to write it down just yet, but what I'm going to write is this is equal to this thing here. And we'll notice something, that this here is a vector. So this lives in R cubed. Okay? And what you can do is you can say, and in fact, this thing here lives in R cubed, and this whole thing here lives in R cubed. So what you can do is actually say that this is true if and only if, for all eta, and for all vectors y, and they're going to live in R cubed, the following is true. So the inner product of this vector here with y is equal to the inner product of this vector y. So why have I done that? Basically, I've done that because this thing is a lot easier to write down than this thing here. And I'm just going to write it down for you. I'm not going to prove this because this really follows from the definition of the gradient. And this is equal to, I'm going to make sure I get this right, because if I don't, that's going to be embarrassing and we're going to have to fix it later. So this is equal to the gradient of q over 4 pi epsilon times by r minus r naught times by the derivative of, this is the total derivative of eta dot producted with y. And the minus sign here basically disappears because you kind of do an integration by parts. So that's what that side is equal to. They're basically definitionally equal to this side, and that's kind of from the definition of the gradient of the vector potential and the definition of the vector potential itself. And then this right-hand side is basically this thing here within this inner product. So what is that equal to? Let me write it down here. I know my screen hygiene is probably not the best right now. This is equal to this thing here. And this is an if and only if statement. So our thing we're trying to prove is true if and only if for all eta and for all y, this integral is equal to this integral. Oh, sorry. I need a y inner product there. So let's be nice to ourselves. We can see that over here we can basically get rid of a q and a 4 pi epsilon because they cancel over here with these two. So basically we have to show that for all epsilon and all y, that and I've also set R0 to equal 0, so we don't have these R0s, which makes our lives a lot easier. So this is equal to y times by r over, and there's a cubed here, r cubed. There's a cubed here, I apologize. Times by eta r, and we need that to equal the integral over all r, so both these integrals are over all r, where r is a vector here, so this is really d3r, times by d eta dr dy. Good, so let me scroll down. You can basically see that if we rearrange this is equivalent to the following. This is equivalent to saying that we want to show that 1 over r times by d eta dr dy minus, and I'm basically combining these two integrals, r times by y over r cubed times by eta r is equal to 0. And this is essentially what this statement here is saying that if this is true here for all eta and all y, then this result, then our desired goal, that is to show that the electric field is equal to the gradient of the electric potential, is true. So now all we have to do is prove this. Okay, so we need to prove this for all eta and y. Good, so how on earth do we do that? Because, well, actually, you may be thinking, this looks nice and simple. So what is the idea? Well, actually, basically the idea is as follows. The idea is to write this integral as the following. Let me. Sorry? Yeah. Okay, good. So basically our job is to, how you would naively prove this is to rewrite this integral as this thing here is basically a total derivative. The problem is that this does not make sense. The reason that this does not make sense is that this derivative is not well defined because this function, basically because the derivative at R0 explodes. So if you could write this integral as this thing here, all would be good because this is 0 basically because it's something called a total derivative, and the integrals of total derivatives are equal to 0. And that's something that's already, standard, and we can take that to be proved. So what we have, because this integral is not well defined in Lean, what we have to do is we have to be clever. And basically the vast majority of this proof is being clever about the fact that this integral, or this quantity here, doesn't have a well-defined integral, and therefore you can't write it as a total derivative. And we do that by introducing in PhysLean this thing called potential limit series, and that is a series which takes in an integer n and gives you the following quantity. Now, you can see that as n goes to infinity, this goes to this, let's call this P of n. P of n goes to 1 over r. Good. And let me see if I can actually find that lemma in PhysLean. This is exactly this statement here, that as n goes to infinity, P of n goes to 1 over r. Good. So that's one thing we have about this, that as n goes to infinity, P of n goes to r. Another thing about this is that P of n is differentiable. So even though 1 over r is not differentiable, and really this is why I'm saying this is not differentiable. In theory, it might be differentiable depending on what eta is, but in general, it's not differentiable, and in general, and like that means you can't prove this in general. So, but in fact, P of n for finite n is differentiable, even though 1 over r is not. And let's scroll up. Let's see where that proof is. This proof is this proof here. And what is more is that its derivative, its total derivative, in the y direction is equal, and this is this result here, is equal to, I'm going to write this down before I explain it, is equal to this thing here. Well, I'm going to write it very slightly differently to how I've written it here. Okay, so that's equal to that thing there, but as n goes to infinity, this thing here tends to and if we look up here, this is exactly the sort of structure we've got here. So, let me make sure I get my eraser correct. So basically, what we are going to do is we're going to look at this quantity, P of n, times by the derivative of eta, times by r, times by y, and we're going to add to that the derivative of P of n in the y direction, times by eta of r. And here's the thing, as n goes to infinity, this thing here, this quantity, let me call this dPn, because this is what in PhysLean is, let me try and find it, is this thing here. What this is equal to, well, okay, so let me start with a simpler result, sorry. So dPn is actually just equal to the total derivative of P of n times by eta of r in the y direction. And you can show that by basically, because this is the use of the chain rule of two differentiable functions. You can't do that up here because things aren't differentiable. And what is more, as n goes to infinity, dp of n goes to, or tends towards, basically the thing we've got within this bracket here. So it goes to, let me write it down. Actually, sorry, that's not 3 over 2, that's just 3 there, times by eta r. Good, so what is true then is that our limit, that the integral that we want to work out, that we need to show is 0, which is this thing here. Well, and actually, let me point out where this result sits within PhysLean. This result is exactly this result here. So it's saying basically, as n tends to infinity of this function here, we basically get back this here. And what this basically means is that this, I'm going to do dot, 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 basically, I mean this thing here, is equal to the limit of n goes to infinity of this integral. And there are a number of things that you have to show to actually show that, you know, this works with integrals. And this is already contained within, let me see if I can find it. Within this lemma tends to integral of dominant convergence. I'm not going to go into that basically because you have to prove a bunch of stuff related to integrals and integrability of things, and I don't really want to get into that. But once you've got this, once you've proved this, which is this result here, you can see that because this thing here is actually equal to a total derivative, as I've written here, that this, and then this total derivative is actually equal to 0, because the integral of a total derivative is equal to 0, then this whole thing is equal to 0. So this is the statement here, that this limit is actually equal to 0. So this thing here is basically saying this function here tends to, at infinity, which is filled at the top, tends to 0. And then this is really putting everything together, because if something tends to, this limit, if it tends to this and it tends to 0, then this thing has to be equal to 0. And that basically concludes the proof. So let me summarize quickly. I understand that stuff like this is a bit complicated to follow, and I'm probably jumping around a lot, but hopefully you can take roughly the idea from it. So what we did is we wanted to prove this thing here. We summarized it by saying, okay, or we simplified it by saying we can consider the R0 equals 0 case, basically because we can commute things with translation. We then said, okay, this is true if and only if it's true on all Schwartz maps, when these distributions apply to all Schwartz maps. And then we said, okay, well, these here things are vectors. We can show that it's true on all inner products of these vectors with other vectors. And then we did some function integral manipulation to rewrite this as this thing here. And then we wanted to prove this, but we couldn't because 1 over r is not differentiable. So we had to use this limit to rewrite things in terms of functions which are differentiable, but whose limit ends up being the undifferentiable things that we wanted in the end. And that's how we prove that the negative of the potential is equal to the electric field. And I want to show Gauss's law and the proof of Gauss's law within PhysLean. So what does Gauss's law say? Gauss's law, so actually let's remind ourselves what Gauss's law says by going over to electrostatics, going over to basic. Gauss's law is this statement here. So it says that the divergence of the electric field is equal to 1 over epsilon times by the electric potential. So in our case, and really here I should have Q and R0, Q and R0, but similarly to what we had before, the translation operator commutes with this delta, so we can actually just consider the case when R0 equals 0 and where Q is general, and I'm just going to write that as this case here. So yeah, this is what we want to show. And how do we show that? This is basically this sometimes confusing result that you sometimes see, that 4 pi epsilon over r cubed times by r is equal to q, or missing a q, q over epsilon times by the Dirac delta function. And, well, in this case, it's actually, yeah, well, it's a Dirac delta function, but really, this should really just be what I was denoting above, delta 0. Let me put a box around that to signify that this is the Dirac delta function centered at 0. So yeah, this is this famous result that you sometimes see, and within PhysLean, the proof that we're going to follow is contained within one of the answers to this stack exchange question. So maybe I can open the stack exchange question, copy and paste. So it follows basically from this stack exchange question by this user here, and this formulation of this problem of this solution basically is completely valid, and therefore allows it to be written in terms of lean, which is all very nice. So how do we show it? So the proof is basically this statement here within PhysLean, and really this is contained in one proof. So I'm going to go through it step by step. So step number 1, we want to show that this thing here is equal to this thing here. So like before, this is true if and only if for all eta we have this thing here is true. And because of what our electric potential here is, this is just eta 0 over epsilon times by q, actually. And we really want to focus on this left-hand side. So what is this left-hand side equal to? And I am looking right here right now. So the first thing this is equal to is, by definition, this is equal to the negative of the integral of q over 4 pi epsilon times by r cubed times by r times by the gradient of eta. And that is really true by definition. You have to do a bit of work to show that this thing here is equal to this thing here, but it is more or less true by definition. So we can then pull some things out of this integral. So we can go q over 4 pi epsilon times by integral over r squared times by the inner product of this thing here. So basically we pulled 2 of the r cubes here out, and we pulled this coefficient out of the integral to get this line here. And then this thing here, so I'm now looking at this line. Oops, actually, no, I jumped a bit forward. We're now looking at this line here. This thing here, so this gradient in the direction of r, which is essentially what this product is saying, is actually equal to the derivative of eta a in the direction of r by a evaluated at r, or at a equals r. And this is something you can just show. It's basically a property of the gradient. So coming down to this thing here, we now want to write this in terms of spherical coordinates. And writing this in terms of spherical coordinates, really I'm going to put an r cubed here to indicate that really here we're integrating over all of 3D spacetime. But now I'm just going to integrate over the radius and the sphere. Well, actually, so I'm going to basically go to spherical coordinates and I'm going to integrate, the radius and what is basically the sphere. And I think I'm missing an r squared there, but I'll correct that in a second. So this r here is now the radius, what's this r is the thing above, and if we do that, what we get is that this thing simplifies to well, let me rewrite this. I apologize for my notation. So this is an integral over the radius, and this is really an integral over the direction. So this is an integral over the magnitude of the point now, and this is an integral over the direction. And then this thing here simplifies to this. And this is basically what this highlighted result on the right-hand side of the screen says. We can do, let me call this hat r thing, let me just call that n. And I'm going to try and really be careful to distinguish between my eta and my n. So we can actually rewrite this now as the following. This is equal to minus q over 4 pi epsilon. And we do the integral over n first. And then we do the integral over the r. And that's 1 over, this should be r squared, 1 over r squared, times by the derivative of eta, where a is evaluated at r. Okay, so that's basically just a rearrangement of the integral, and this is this thing here. And I'm just going backtrack in a second just to see something. Really, you actually have another r squared here. Because when you go, yes, good. So here you have another r squared, and that really comes from writing these things out. So that comes from the mesh. So here you have another r squared, and then this r squared cancels with this. And you are left with this integral here. And this is from 0 up to infinity of the eta a times by n dA. And basically what happens now is that you rewrite this, you basically say, okay, eta, because it's one of these nice Schwartz functions, it decays really sufficiently well that this decays at infinity to 0, and when at 0, basically because this a here, you just get 0. So this whole integral, because it's an integral of derivative here, is basically equal to this thing here. And this is then equal, of course, to q over 4 pi epsilon times by eta 0. And then we integrate over the sphere, which is this dn thing. And the integral over the sphere is equal to 4 pi. Good. And that is then, of course, equal to Q over epsilon eta naught. And that is precisely, if we scroll up a bit, equal to what we had on the right-hand side, what I wrote down here. And that's how you prove Gauss's law in this case. And this is this big, long proof in PhysLean, and that's kind of how it does it. I apologize that I mucked up with regard to the measure. The measure is a bit complicated, actually, of what you should integrate over with regard to the volume, which is why I got a bit confused. What we're going to try and do in the future in PhysLean is make the API around spherical coordinates better, so this is easier to do things with regard to spherical coordinates. And let me quickly talk about Faraday's law, which is obviously this thing here. Faraday's law. In PhysLean, Faraday's law is really simple to prove, given what we've already proved, because it basically says that the curl of the electric field is equal to 0. But because we've already shown that this electric field is equal to the negative of the gradient of the negative of the gradient of the potential. So this is equal to this thing here, and then this is equal to this thing here. And there is a general result that a curl of a gradient is equal to 0, and that proves Faraday's law. And this is, in PhysLean, this is a two-line proof. Very simple. Great. And then this informal lemma. So if you want to get involved and you want to help, this is something that you could do. You could help prove that the electrostatic field of a point particle is rotationally invariant. So hopefully that was understandable. Hopefully that was good. Hopefully you could follow this. I'm trying to experiment, the best way to record this type of video, going through something in PhysLean. I understand that a lot of this is probably quite confusing, so I apologize for that. But hopefully you've learned something from this, and thank you for watching.